Hello, everyone, and welcome to Lecture 3 in our atomic spectroscopy module. This is going to be on interferences, quality control, and industrial case studies. So the learning objectives are seen here. So we want to be able to characterize the different interferences. We want to be able to compare the different lamps. We want to be able to compare different methods of overcoming that. And of course, looking at a real industrial study by the end of it. So what is interference and why does it matter? So the definition here of an interference is really anything which causes a deviation in our measurement, okay? So that whatever causes the signal to change from the true signal can result in positive, i.e. enhancement, or negative suppression, and it's usually systematic error and can often be overcome. If we don't correct for it, however, we can create false high or low results, which of course can be problematic because if you're, for example, internal monitoring is showing that you're in compliance with government regulations, but if a government environmental agency comes along and measures it and finds out that you're actually in deviation and not in compliance, then you've got a significant problem, and it could have been avoided, which can cause results in wrongful compliance clearance or unnecessary enforcement actions. Okay, so there's three main categories. There is spectral interference, which is where another species absorbs or emits at a line very near the analyte wavelength. Chemical interferences, which cause the changes in the environment, which can result in differences in the amount of free atoms, which can be actually reaching the beam. And then matrix interferences, where we have bulk physical chemical properties which affect signal transport from the sample to the detector. Okay, so the key diagnostic question is, does the spike recovery fall between 85 and 15%? If not, an interference is present and must be identified and corrected. Okay. So the common spectral interference number one is line overlap, which we can see over here on the right-hand side, which is an overlap of an interferent with an analyte inside of the slit bandpass, which creates an unnatural broadening of the emission line. So the cause here is a matrix element's absorption or emission line coincides with or lies within the monochromator bandpass of the analyte line. So the detector cannot distinguish the two signals, and so the result is a positive interference where the analyte signal is too high. So common examples are, for example, in atomic absorption spectroscopy, iron overlapping with lead. So they're, of course, quite well resolved in terms of their wavelengths, but the result of the monochromator, they're within the same band pass. And so it results in a sort of an interference. And we also can have it with ICP-OES. There's many there. There's aluminium, which can overlap with vanadium, calcium, which can also have so many lines, many overlap with trace metal analytes in dairy and bone ash digests. So, like for example, calcium is broadly present in dairy products, and so it can interfere with the ability to actually measure contaminants present in dairy products. Okay. So this is an issue, especially with emission spectroscopies, primarily because you're getting a lot of elements at the same time. So the corrections here are to select an alternate interference-free analytical wavelength. We look at inter-element corrections to measure the interfering element separately. We can subtract its known contribution from the apparent analyte signal. And we can also look at chemical separation, where we remove the interfering element by precipitation, extraction, or solid phase extraction. Spectral interference number two is looking at background absorption. So this is non-atomic species in the flame or the furnace gas phase. So this can be caused by like not incomplete atomization of different molecules or refractory elements. Okay, so this is unvaporized particles scattered from the HCl beam. It's equivalent to absorption. We have molecular absorption, so for example, flame gas molecules or matrix fragments and so on, which can absorb over broad wavelength ranges because of the presence of those bonds causing vibrational and rotational energy levels to be an issue. So the result here is a positive error where the measured absorbance is again too high. This is particularly severe in GFAS, where the matrix is vaporized simultaneously with the analyte. And so the three background correction methods are to use a deuterium lamp, the Zeeman effect, or the Swift HFG. So each is described on the next slide. So the deuterium lamp background correction is to use a second broadband UV source alternated with the HCl beam. So the HCl beam absorbs, of course, the atomic signal in the broad background. The D2 measures only the broad background. So the atomic line is too narrow to absorb a significant fraction of the wide D2 source. So the net signal here is equal to the HCl absorbance minus the D2 absorbance. The limitation here is it's only really effective in the UV and inaccurate for structured wavelength dependent backgrounds. The Zeeman effect background correction. So this is using a strong magnetic field applied to the furnace or the source. So the Zeeman splitting separates the atomic line into pi and sigma components displaced from the analytical wavelength. The sigma components then measure the background, whereas the pi measures the signal plus the background. It's the most accurate. Handles structured backgrounds on high background levels. It's preferred for GFAS. Okay. Then we have the Smith-Hiefte BC. So the HCl is operated at alternating low and high currents. At high current, we have self-reversal, dense cloud of cool atoms at the cathode surface, which is absorbing the lamp's own resonance line, creating a dip at the analyte wavelength. We have a low current, so there's a normal signal and high background, so this can result in background only measurements. And the net is that we have a low current, high current signal, and so this is typically less expensive than Zeeman and adequate for moderate backgrounds. Okay, so if you're working only in the UV, then D2 is good. Otherwise, you'll have to look at Zeeman or the Smith-Hiefte. So the Zeeman effect, what is it? So this is the magnetic splitting of atomic lines. So the normal Zeeman effect is that without a magnetic line, we just get one absorbance at whatever the wavelength happens to be. But if we do apply a magnetic field, so between 0.5 and 1 Tesla, we see that the line can be split. Okay, so we have three components. We've got the pi component, which remains at the wavelength, the original wavelength, which polarized parallel to the field. And we have the sigma plus and sigma minus, which are shifted either shorter or longer wavelengths, which are perpendicularly polarized. So the sigma plus or minus components no longer coincide with the analyte absorption profile, and they measure only the background. The measurement cycle, then, how do we do that? We turn field off and on, and then we look at the net signal that's going on. So when do we choose between the Zeeman background correction and the D2 lamp background correction? Well, this is when is each appropriate. So the Zeeman is preferred in GFAS, whereas the D2 is only really possible whenever we have clean matrices with low backgrounds and we're working primarily in the UV and we have a cost constraint because it's much cheaper than the Zeeman equipped ones. But elements with high sensitivity not requiring structural background removal are also okay. The Zeeman is preferred because it works at every wavelength from UV and onwards. It handles structured backgrounds pretty well. So that's where we have like a lot of different bands co-eluting with the molecular fragments in GFAS. We have the D2 background correction, which subtracts a broadband baseline. So it cannot distinguish between a structured molecular absorption band with a smooth background and overcorrects or undercorrects. The background and analyte measurement use the same optical path, so there's no risk of spatial misalignment between the two beams. And so the net result here is the Zeeman gives more accurate correction of complex matrices, such as blood, urine, food, and solid digests. So in summary, we use the Zeeman for GFAS with complex matrices, and D2 for any routine flame analysis with atomic absorption spectroscopy and clean matrices. So if we look at a reminder for the Smith-Hiefte BC, a reminder, so at high HCl current, the lamp line undergoes self-reversal, i.e. a dip at an original wavelength due to the cool atoms at the cathode face absorbing the emitted line, and so we have alternating low and high current gives total background signals respectively. There's a moderate cost, however, it does not require an extra lamp or a strong lamp. And it's effective for many routine matrices, but not as accurate as Zeeman for heavily structured backgrounds. Chemical interference 1 then, which is ionization. So this is typically caused by the thermal ionization at high temperatures of the analyte atoms, okay? So we can have issues here where the metal absorbs additional energy and becomes an ion. So ions do not absorb at the same neutral atomic resonance lines. And so we have fewer neutral atoms in the beam, which results in a lower signal. Okay. This can be a bigger issue at higher flame temperatures, like the N2O acetylene mixture being at high temperature, which causes more ionization. Okay. The most affected elements are mostly group one and two elements, where they have mostly group one elements, where they have pretty low ionization potential. So the correction here is to use an ionization suppressor, which is typically to add a sacrificial element. So that's something which has an even lower ionization potential, which will be ionized first. So it kind of works through Le Chatelier's principle in the flame. So we've obviously got our neutral atoms. And then those are in an ionization equilibrium. So if we add an excess of the cesium ions, what that does is it tends to add excess electrons, which results in the neutralization or the creation of more potassium atoms, which restores the signal. So, the cesium, it's a double-edged sword. So like the cesium absorbs the energy to be ionized to produce electrons, and those electrons then combine with any potassium ions in the gas, which causes those to form the neutral potassium atoms again. So the practical consideration here is to add the cesium chloride at a certain concentration to both standards and samples for sodium, potassium, and lithium. And so we look at barium analysis and flame atomic absorption spectroscopy of flame OES. Chemical interference number 2 are refractory compound formations. So sometimes an analyte mixture reacts with the matrix components to form more thermally stable compounds, which cannot be fully atomized. So what we usually do here is we have some sort of a releasing agent. So we're making use of hard soft acid base theory to find something which will bind preferentially with the problematic anion, for example. That will ultimately depend on what form your thermally stable compound is. So for example, in the calcium hydrogen phosphate, you're probably going to add some sort of a lanthanum there, which will form a more stable phosphate compound. You can also use chelating agents, so we can complex the analyte with EDTA, for example, which will decompose cleanly in the flame. And then we can have a hotter flame, for example. But the problem with the hotter flame is that you also potentially increase the concentration of ions in the flame. The third chemical interference then is volatilization in GFAS. So during this process, one of the issues is that you're volatilizing everything sort of simultaneous inside of the GFAS, whereas you don't have that same problem in the flame. So the matrix components here co-volatilize with the analyte, changing the effective pyrolysis temperature window. So the example here is that lead in chloride matrix is lost during pyrolysis before the organic matrix is destroyed. We can also look at carbide formation. Some elements form graphite carbides with the furnace wall. And so we also look at memory effects of the previous sample deposits on the graphite. So this is an incomplete cleaning process. So what we can do here to fix this is to use what's called a chemical modifier, or to try and control the pyrolysis temperature better, or to look at platform atomizations. This is through our Lvov platform. And so this delays atomization until the furnace wall reaches thermal equilibrium, reducing matrix vapor pressure effects. So matrix interferences and calibration-based corrections. So we can have some physical effects, such as viscosity differences. So high viscosity samples, so for example, sugary food digest, high glycol solutions, and so on, pump and nebulize at a different rate than aqueous standards, which creates a different analyte flux to flame ratio. We can also have high total dissolved solids, which can result in the blockage of the nebulizer, which can be problematic. We can have high salt deposition, or maybe we can have ICP torch file. So our organic solvents, so we want to change the nebulization efficiency. We want to look at flame stoichiometry and plasma loading, and this can cause severe enhancement or suppression of the signal. Physical corrections can also be done, so we can use matrix matching, so add the same matrix components to all the standards. So for example, 5% nitric acid, same salt level, dilution, reduce matrix effect to below the threshold of significance. So typically greater than or equal to 5 times the dilution. We can keep the total dissolved solids also low, or we can use a peristaltic pump to deliver precisely controlled flow rates. Okay, so this can hopefully try to suppress any of those matrix effects. So the standard addition method can also correct the multiplicative matrix effects, just trying to avoid matrix suppression effects. So in standard addition, both the native analyte and the added spikes experience the identical matrix, and so the slope already reflects the suppressed sensitivity. The extrapolated intercept gives the true CX. So then spike recovery formula is seen here, and so this is the quality control protocol for our atomic spectroscopy. So we minimum required quality control elements are a calibration blank, as usual. Calibration standards, minimum 3, better 5 or more. We want to have calibration verification standards. So these are going to be an independent source checked after every 10 samples. So you have something that you know the response of, and that you will test in between or during your measurement of the other samples, so that you can be sure that everything is, or you can improve reliability of your method. You can also do matrix spiking. We can duplicate systems. We can use certified reference materials, and we can make sure to use a procedural blank. Okay, so the spike recovery formula is given over the right-hand side here, which is the percentage recovery is equal to concentration of the spike versus minus the unspiked over the amount that was added times 100% to see if you're getting back an accurate reading on the amount of analyte that you had versus what you think you have versus what you actually have. So this is all ISO accredited laboratories such as DNR, FDA, DOST will all document and archive all quality control data for each reported result, and a field QC check invalidates the entire batch. Okay. CRM selection. So you need to choose one that's just got a similar matrix. So for food, we use bovine liver or muscle. For water, we'll use NIST SRM 1643E. And so we never use a aqueous standard as a CRM for digested food because obviously it's not at all similar. So what happens if we have a batch failure in our quality control? How do we troubleshoot that? So if, for example, we have done our quality control and our CVS is outside 90 to 110%, what should we do? Well, we should recalibrate immediately with fresh standards. If the recalibration passes, then rerun the samples which are affected since the last passing CVS. If it's still failing, check reagent expiry, instrument drift, and so on. Then after that, invalidate the batch if the root cause cannot be determined, resample, redigest, rerun. Matrix spike recovery outside of the 85 to 115%. What is the cause for this? So if we look at low recovery, we will have signal suppression. So we look at either chemical interference, a physical matrix effect, or something else, which means we have to take some sort of action, which is to switch to standard addition and investigate the modifier. If we have a higher recovery, we'll look at signal enhancement or contamination. So ionization suppressor effect, so there's an unequal sodium between samples and standards. The contamination from the reagents is a problem, or can be that there's a need to clean glassware or the environment. What happens if my certified reference material is outside plus or minus 2 times the standard deviation? We have what's called a method accuracy problem. So the systematic error in sample preparation, so the digestion efficiency, dilution error, contamination during digest, and so on. We look at the wrong element-specific conditions. So for example, we have pyrolysis or bad atomization, temperature for GFAS, the wrong analytical line for ICP-OES, and so on. We want incorrect calibration range or standards preparation. So the action here is to repeat the full method on a second certified reference material. Both failed in the method, of course, will need to be reevaluated. So what is the golden rule of batch acceptance? That no result may be reported from a batch in which any quality control check has failed and the cause has not been identified and resolved. This applies regardless of client deadlines, sample urgency, or volume of work. Reporting results with unresolved quality control failures is a serious breach of ISO 17025 accreditation requirements. So you need to make sure that you follow quality control. You don't do it at the end, you do it as you go along. Okay. So let's look at our worked example number 1. All right, so we look at GFAS limit of detection and limit of quantitation for blood lead. Okay, so a GFAS blood lead method is characterized. So we have 10 replicate blank measurements, matrix matched, no lead content. Then we have calibration slope from those, which is given. So we want to then calculate the absorbance in the blood and also the standard deviation. We want to calculate the limit of detection using IUPAC standard, 3 times the standard of the blank, divided by the gradient. We want to also know the limit of quantification, which from IUPAC is 10 times the standard deviation of the blank over the gradient. And then we want to look if we have made a fit for purpose assessment against DOH action level of 5 micrograms per deciliter for children. So why GFAS for blood? So blood lead ranges 2 to 100 micrograms per deciliter in whole blood. After 1 to 4 dilution, we have 4 to 200 micrograms per liter, sorry, in solution. And so flame atomic absorption spectroscopy limit detection is around about 100 microliters. So this is completely insufficient for normal blood levels. So GFAS then limit of detection is sub-micrograms per liter, which is required. We can get down to nanograms per liter, so that's perfectly fine. And since we're only doing one element, GFAS is fine. We don't need to go to ICP-OAS or anything. Okay. So blind statistics are shown there, which is computed from the 10 replicates. The limit of detection is 3 times the standard deviation of the blank, which is calculated up here over the gradient, which is here, the M value. And so we see the limit of detection is 0.073 micrograms per deciliter, which is below, the normal range. Okay? Limit of quantitation is 10 times the standard deviation of the blank over the gradient. So the limit of quantitation is 0.242 microliters per deciliter, which is still well below the normal lead blood range, okay? And so we check if we have a fit for purpose assessment. So action level is 5 micrograms per deciliter. Our limit of quantitation is 0.242, which is equal to 20.7. So the method quantifies less than or greater than 20% the below action level. And so we say that this method is indeed fit for purpose. Worked example number 2, spike recovery for cadmium in seafood. So the problem here is the cadmium is determined in squid digest by GFAS. We have our calibration slope, we have our quality control measurements. We want to calculate the unspiked cadmium, the spiked cadmium, the spike recovery, and then make a decision on whether or not this is acceptable. Okay. So the solution here is that we calculate the unspiked. So that's going to be our 0.182 over 0.1420, which gives us a concentration of 1.282 micrograms per liter. Then we calculate spiked here sample. We see the spiked recovery, which is 100%. So great spike recovery. So that means our decision is 100%, which is well within the 85 to 15%, 115%. So the results are reportable. The batch is accepted. So there's no matrix effect from the squid direct digest, and so the recovery reflects the analyte alone, not the matrix. Number 3, IEC correction for iron overlap on lead. So lead can be determined at 220.353 nanometer resonance line by ICP-OAS in iron high borehole water, where the iron concentration there reaches quite a high concentration. A pure iron solution test shows that 1 microgram per liter iron produces an apparent lead signal equivalent to 0.0240 micrograms per liter at 220.353 nanometers. So this is the IEC coefficient. And so the sample measures that value. And so we calculate the IEC correction term, the true lead concentration, and we ask what would have happened without the IEC. So the IEC correction term is the delta, the change in the concentration of lead. So delta concentration of lead is equal to the correction factor times the concentration of iron, which gives us 1.2 milligrams per liter. We correct then the lead concentration. So that's going to be the concentration of lead is equal to the apparent minus this delta CPB, which is equal to 0.087 minus 1.20, which gives minus 1.11 microgram per liter. And so the corrected value is around about 0, so negative within the sample noise. There's no detectable lead in the sample. The entire lead signal was caused by iron spectral overlap. And so without the IEC, the analyst would have reported that there was lead, 0.087 micrograms per liter, which is 8.5 times above the DENR drinking water limit of 0.010 micrograms per liter, which is a completely false non-compliance finding, and the water is perfectly fine. So how do we actually determine these IEC coefficients? What is the experimental protocol? So we have a step-by-step determination of this IEC coefficient, this Ki to A. So we want to identify potential interfering elements from the sample matrix. So from the sample digest composition or prior knowledge, we want to prepare a series of pure solutions of the interfering element I at concentrations spanning the expected sample range, so 0, 1, 5, 10, 50, 100 micrograms per liter for iron. We want to measure the apparent analyte signal at the analyte wavelength in each interference solution, so no actual analyte present. And we want to plot A versus I, and so the slope of this line is the IEC coefficient, okay? So, which is given below. So when IEC fails or cannot be applied is when the relationship is nonlinear, so very close spectral overlap. The interference concentration varies unpredictably between samples, and in these cases, we switch to an alternative interference-free wavelength or use a chemical separation steps. So most IECP OES software introduces and includes a database of pre-measured IEC coefficients for hundreds of element pairs, and the analyst must verify these for their specific matrix and wavelength selection. So don't always fall back on the database. It might not always work perfectly for your exact setup because things change with maintenance over time. So here's work example 4, which is looking at the ionization suppressor for potassium in fertilizer. So potassium is determined by flame OES at 766.5 nanometers in the fertilizer extract containing this much sodium. Calibration with and without the cesium chloride is shown here. Remember, cesium chloride is a suppressed ionization suppressor for potassium. So we can see the slopes with and without the cesium suppressor. And so we can see then the concentration with and without. We see that the concentration without the cesium chloride is reported as being higher than with. And so without cesium chloride, 300 milligrams per liter sodium in the sample partially suppresses the potassium ionization, enhancing apparent potassium signal relative to the pure aqueous sample. Cesium chloride locks the ionization equilibrium, given the correct result of 6.31 milligrams per liter, and the uncorrected value is just too high. So let's look at our case study. So this is blood lead surveillance at a Bulacan smelter. So a secondary lead smelter in Bulacan employs 85 workers, okay? So Republic Act 11058, the OHS, the Occupational Health and Safety Act, requires periodic blood lead monitoring, okay? So the blood limit is 40 micrograms per deciliter. Above that, you need to remove them from the exposure at 50 microliters per liter, 50 micrograms per liter. Sample prep here is to digest the blood in nitric acid and then do a tritone X10, X100, sorry. The method then is GFAS at 217 nanometers, peak area Zeeman background control. It's essential for complex blood matrix backgrounds. So the selected results here, so we have 4 workers. We see their blood levels. 2 of them need to be removed from the exposure. 1 needs to be sent for medical treatment, and 1 is open. Okay. So we have analytical justification for GFAS here. We're only measuring 1 sample at the end of the day, and we're doing pretty well. Okay. We need to do quality control though. So we obviously do our matrix spike, and we get a recovery percentage using the NIST SRM of 97.3%, which is a pass. We look at the matrix spike recovery, 101.5%, which is also a pass. And Zeeman background correction verified by matching the D2 background correction at low background levels. Okay. Case study 2 is looking at cadmium heavy metal contamination in rice from a mining affected province. So this is there's concern over cadmium contamination in rice grown near the former Mar Copper mining trailings in Marinduque. So 50 milled rice samples are microwave digested and they're tested. So there's an interference problem identified. So the rice digests are at high phosphorus, the rice digests are high in phosphorus from phytic acid. So in GFAS furnace, the cadmium hydrogen phosphate forms during the pyrolysis at low temperatures. And so this results in early volatilization of the cadmium. So this means that without a without a modifier, we get a very low concentration, which would potentially be a field, okay, that's outside that 85% threshold. So what we do is we add an ammonium hydrogen phosphate, which is co-injected, which stabilizes the cadmium as a thermally stable phosphate complex. And so then the pyrolysis temperature is raised to 500 degrees Celsius, okay? And so this means that we're able to do our quality control checks properly. So after correction, we see 12 out of 50 samples exceeded the 0.4 milligrams per kilogram limit. So without the corrections being suppressed by 25 or 29%, only 5 out of 50 would have been flagged. And the interference caused the 7 sample undercount direct food safety implications. Okay, so this is why we really need to make sure we do our quality control, why we really think about interferences that might be present. Okay. So the interference diagnosis, so is our spike recovery out of range? If it is yes, we run our diagnostics, such as our CRM, our duplicates, or our blanks. Do we have any spectral interference? Then yes or no. If no, we continue to look at chemical interferences. If yes, we alternate the wavelength, the IEC correction, the BC method. We have the chemical interference, yes, then we look at ionization suppressor, releasing agent chemical modifiers. No, we look at matrix, physical matrix interference problems. Then we look at the matrix match, the dilute sample, peristaltic pump. And if we go to standard addition, internal standard, or both, if we have these matrix problems. So that's the end of module 3. We've looked at foundations, instrumentation, and interferences. And the next we'll do that assessment. So we'll check our practice problems there. So problem 1, 2, and 3, 4, and 5. Make sure to have a go at them. The solutions will be posted before any assessments. Thank you. Any questions? Please post them below.